Okay, so we will start off from where we left off yesterday. Um, okay, so yesterday we stopped midway on proving the Babai-Frankl-Simon theorem, which was trying to show a lower bound for the randomized complexity of disjointness. So we proved one of the main lemmas in the proof, except for a claim that was included. So what was the main lemma again? The main lemma was that if uh, if a particular rectangle is an almost epsilon unbalanced one rectangle, then either the number of rows of that rectangle is small or the number of columns of that rectangle is small. And small was defined as 2 power minus c square root n fraction of the total number of rows or columns. Okay, so on the way to that, we had used a claim. So what we will do today is we'll first prove this claim, after which we'll prove the theorem using the lemma. And again, that will also require another result, another small result. So we'll complete the claim, proof of the claim, then we'll prove the theorem, and then we will prove the other small result that I mentioned. It is called corruption bound. So we'll prove the corruption bound, and that's what we are going to do for today. So it's probably going to be a bit shorter lecture than yesterday, and I guess you may be concerned that these kind of the material is getting more and more difficult, but don't be too concerned because by what I can tell from whatever I have planned to cover in the remaining lectures, I guess this is probably the most involved set of lectures. Meaning, this result is probably the most involved set of result. Even this is not that difficult, but then certainly it would have been easier to do this result in the live class than this mode. But don't the next lectures may be a bit simpler than this. Okay. Okay, so let's see what was the claim again. The claim again was suppose there is a no. The claim was that there exists a C prime such that if there is a set S prime of size at least half times 2 power minus C prime square root n times n to square root n, then there exists x1, x2, x3 up to xk, where k is n square root n by 3 elements or sets in S prime such that each one of these sets brings in at least square root n by 2 new elements, or in other words, each one of these sets intersects with at most square root n by 2 elements with the previous xj's, right? So the proof is not that difficult. It's just using induction. So we'll just show that if L is we'll just show it using induction. Suppose x1 to xl are in S prime, and suppose L is at most square root n by 3. Then we will show that if it is strictly less than square root n by 3, then we will show that we can add another x star to S prime such that x star intersects in at most square root n by 2 positions in the previous xi's. Okay. So if there is x1, x2 up to xl, where L is strictly less than square root n by 3, then we can add an x star which to this set which meets the required condition. And the base case is trivial because when you add x1, there is nothing. So it already meets this property. Okay. So now, so how is the proof going to go? What we are going to do is, if L is strictly less than square root n by 3, we look at how many elements are there in the union of x1, x2, x3 up to xn. So we don't know anything we don't know anything for sure, but we let us take the worst case. So L is at most square root n by 3. In fact, it's strictly less than square root n by 3. And each one of these sets contain exactly square root n elements. So the total number of elements is at most square root n times square root n by 3. Right? This is the worst case, which is n by 3 elements. Now, consider the x, that is the x's that are there in S prime, right? So consider those x's that intersect with z. So z is a union of all the existing xi's. So consider those x's that intersect with z in at least square root n by 2 elements. We don't want such x's, right? What we want is x intersection z should be at most square root n by 2, strictly less than square root n by 2, right? This is what we want. So this part is the z, right? We don't want such things. So what we will do is we'll count the number of such x, and we'll show that this count is strictly less than the size of S prime. So we'll count this number of such x that intersect in at least square root n by 2 elements with in z, and these are not the kind of x that we want. We want the opposite kind of x. But even if when we enumerate all such x's, the total number of such x's are at most or strictly less than the size of S prime. So that means that there are other elements in S prime that don't satisfy this condition, and these elements can be will be the chosen x star. Right? That's what I have written here. So, and that x star could be added, and that will satisfy this property. Okay. Okay. So now let us do the counting. The number of x prime such that the number of x in S prime such that x intersection z is at least square root n by 2. Okay. So z is already there. Now, what we can do is, now how many elements does it intersect with z? Suppose, so we know that it must intersect in at least square root n by 2 elements. So let us call the intersection size as I. Now we know that I is at least square root n by 2, but maybe more than that. I cannot be more than square root n because x itself is of size square root n. So I can be anything in between square root n by 2 to square root n. And now we want to choose the I elements that intersect, that have which are both in x and z. So we know that x intersection z is I, and we know that the size of z is at most n by 3. So in the worst case, this can be done in n by 3 choose I possible ways. And then we pick the elements that are not there in z, and this can be done in 2n by 3 choose square root n minus I ways, right? Right, so I think there is a small thing to note here. So the question is, if the size of z was slightly lesser than n by 3, then what would have happened of this product? Let's say it was n by 4, then is n by 4 choose I times 3n by 4 choose square root n minus I upper bounded by this? I'm guessing so, because I think the closer we are to the middle, so I think this is an upper bound of the product of these two binomial coefficients. So the point that I'm making is z is of size n by 3 or lesser, and you could have the size of z here and n minus size of z here, but this is maximized when size of z is n by 3, I think, is exactly n by 3. So that's why this is a upper bound, right? Now you can easily see that I runs from square root n by 2 to square root n. Now, when I increases, we are taking, we will have, when I increases, the binomial coefficient, the first binomial coefficient has a becomes larger, but the second binomial coefficient becomes smaller. But this becomes, the second binomial coefficient becomes smaller, much smaller than this becomes larger. So when I increases, this whole term, this whole thing becomes smaller and smaller. So the product of these two things is maximized when I is the smallest. And I is the smallest means I is square root n by 2. So if you ignore the sum for a moment, the product is maximized when I is square root n by 2, and that's what we have here. And the summation runs through square root n by 2 plus 1 terms. So I'm just replacing it with the maximum times square root n by 2 plus 1. Okay. So this is the number of ways in which you can choose an x such that it intersects with at least square root n by 2 elements of z. We have we first choose the size of the intersection, and we choose the intersecting elements from z, and we choose the non-intersecting elements from the z complement. And now we have a calculation that is similar to what we saw yesterday. So we have the product of two binomial coefficients and another term here, square root n by 2 plus 1. And we can, using Stirling's approximation, similar kind of ideas. Again, I have a page at the end where I do this calculation. I just explained it very briefly. It's basic algebra that you can verify. We get that this is at most 2 power minus 1 minus c prime square root n and choose square root n. And this is the size of s prime. So the total number of x that intersects with z in at least in square root n by 2 locations, the number of such x's strictly less than the size of s prime. So there are other elements in s prime which we can add. So such an element in x prime will be, let's say s prime will be the desired x star, and that we can add. And that is the induction step. So we first choose x1, and then once we have an x1, we can choose x2 because of this. And once we have x1, x2, we can choose x3 because of this. And at each time, we will make sure that it intersects with previous elements in at most or strictly less than square root n by 2 locations. And this keeps getting maintained. All we want is that the total number of sets that are chosen till now is strictly less than square root n by 3. So we can get up to exactly square root n by 3 sets in this way. Okay, so that completes the proof of the claim. Okay, so now we have the main theorem, which was that the randomized complexity of disjointness was at least square root n. So let us move to the main theorem. Okay, so what was the lemma again? So just revisit the lemma. If R is equal to S cross T. Okay, so this is all with the context, with the setting that we already set yesterday. We have a distribution mu, which was, we pick each element, x to be equally likely from all the sets that have exactly square root n elements, and same for y. So if a set has exactly square root n elements, we pick that with probability 1 by n choose square root n. Okay, so what was the lemma? If R is an almost epsilon unbalanced one rectangle, in other words, the measure of, so R is a one rectangle, the algorithm or the protocol reports 1. Now, what fraction of R are actually zero entries? Meaning, what fraction of the entries in R are actually zero entries? What fraction of entries in R are not disjoint but are being reported as a disjoint. If this fraction is at most epsilon, so in other words, the measure of R intersection, the inverse image of 0, is at most epsilon times the measure of R, then it is such a rectangle. If it is such a rectangle, then either S or T is at most 2 power minus c square root n times n choose square root n. That is the lemma. Okay, now let us see how this implies a bound on the measure of R. So either S or T is small. So let's say that T is smaller than S. So because T is smaller than S, then T is going to be at most 2 power minus c square root n times n choose square root n. Now what is the measure of R? Measure of R is summation of the measures of all the elements in R, which is S cross T. And now we know that this is a product distribution. So I could decompose into mu of ST as the measure of lambda of small s times rho of small t, which was the respective distributions for the rows and columns. And the joint summation can be split into a product. So I get this and I get this. And the summation of the measures of all the rows in S, we don't know what that is. We don't have any bound on the number of rows in S. But we know that the total, if you add up the measures in all, you get 1. So it cannot be more than that. So if you replace S by all the rows, you get 1 here. So that is upper bounded by 1. And the columns, we know that T contains at most 2 power minus c square root n fraction of the total number of columns. So, or the total number of columns that are being considered. So this corresponds to a measure of 2 power minus c square root n, because that is the fraction of the columns that are present in T. Hence, the measure of R is upper bounded by 1 times 2 power minus c square root n, which is 2 power minus c square root n. So if R is a almost epsilon unbalanced one rectangle, then the measure of R is at most 2 power minus c square root n. Right? So this follows from the lemma that we saw yesterday. Now I will state a theorem or a result called corruption bound. What it says is that consider all the almost epsilon unbalanced one rectangles. And consider its measures. If the maximum measure of such a rectangle is alpha, and suppose epsilon is strictly greater than epsilon prime greater than 0, then 2 power the distributional complexity of, okay, so, just one more thing. So suppose we are considering a function f and a 0, 1 function f. Now if for that function f, the maximum measure of an almost unbalanced one rectangle is alpha. Okay, and suppose one rectangle is alpha, and then for such a f, we have 2 power the distributional complexity of f with respect to the distribution mu. Right? There is always this distribution mu that we are talking about of any distribution mu, and the error parameter of the distributional complexity is epsilon prime. Okay, so note this change. The reason I'm using epsilon prime here is that we have already used epsilon for the we have already used epsilon here as the epsilon unbalanced parameter. So for this we used epsilon. So I'm using epsilon prime here. Okay, so I want to keep the already defined notation as consistent. So here I'm using epsilon prime. Now the 2 power the distributional complexity with respect to mu and epsilon prime of f is at least 1 divided by alpha times the measure of f inverse of 1 minus epsilon prime divided by epsilon times 1 plus epsilon. Okay, where alpha is the maximum measure of an almost epsilon unbalanced one rectangle. This is the corruption bound. Okay. Okay, this is the corruption bound. I'm just wondering if we are assuming because a one rectangle makes sense only when there is a protocol. Okay, let's move on. Let's sort this out later. So suppose the maximum measure of an almost epsilon unbalanced one rectangle is alpha, then we have this bound. And now you can see how the proof is going to go. Okay. We will use this result at some very soon, and this gives you a lower bound in the distributional complexity of f with respect to these parameters. So here f is going to be disjointness, and we already know the maximum measure of an almost epsilon unbalanced one rectangle. We just saw that it is 2 power minus c square root n. Right? So alpha is 2 power minus c square root n, and so 2 power distributional complexity with respect to mu and epsilon prime of f. So f here is disjointness, is alpha is 2 power minus c square root n. So 1 by alpha is 2 power c square root n. And what is the mu of f inverse 1? So what fraction of inputs, what measure of inputs are one inputs or result in where the function evaluates to 1. So it is so what fraction of x, y are disjoint? And we already saw yesterday a crude bound that it is roughly, it looks like 1 by e. Right? So 1 by e, it is a constant, something like 0.3 something. So you may be concerned that this is a rough approximation and not an exact computation, but that's okay. So all we want is something like 0.3 or something like that, some constant, which is 0.3, 0.2 or something like that. Now minus epsilon prime by epsilon times 1 plus epsilon. So notice that epsilon prime is less than epsilon. So this quantity is, so you can choose epsilon prime to be much smaller than epsilon. Let's say it's 1 by 100 fraction of epsilon. So this thing is something like 1 by 100. And 1 plus epsilon is almost like 1 because epsilon itself is small. So this entire thing can be made something significantly smaller than 1 by epsilon, 1 by e. So that this thing is going to be some constant like 0.2 or 0.1 or something, right? And now we can see the distributional complexity of disjointness with respect to mu and epsilon prime is, you can just take logs here. If you take log, you get that on the left hand side we have the distributional complexity, and the right hand side we have c times square root n times log 2 of this thing. And I just explained that this quantity inside the square bracket is going to be something like 0.2 or 0.1, so that's a constant. That's a constant. And I think there's a very small mistake here. So when you take the log of this, it should be c square root n plus this, right? Not product. It should be this plus this. So but the point is that this is a constant. There's some constant that doesn't that will be dominated by this term. So it is, the distributional complexity is c square root n. And okay, so there are more typos here. All of this should be made square root n. This square root n, this square root n, and this square root n. Let me just do one thing. I will fix it in my notes, and I will rescan it and share it. So all of these should be square root n. Right? So that is so basically the distributional complexity is square root n. Hence the randomized complexity by the von Neumann theorem is square root n with public randomness. So the private randomness is only going to be worse. So that's also going to be square root n. Okay. So that completes the proof of the Babai-Frankl-Simon theorem. Now what we have left unproved is two things. One is the proof of corruption bound, which is going to be very easy, and the other is going to be this Stirling thing, which we've already seen one instance of yesterday, and it's going to be very similar. So first, let us get to the corruption bound. Okay, what is the maximum measure? Okay, what does the corruption bound say? The maximum. So consider a function f. If the maximum measure of an almost epsilon unbalanced one rectangle is alpha, then for epsilon and greater than epsilon prime both greater than 0, we have this. Right? We have already explained this. So consider a protocol, a distributional protocol for f with over the distribution mu and with error parameter epsilon. Now suppose the cost, so now whatever the protocol, the cost is partitions the space into 2 power cost times rectangles, right? It partitions the entire thing into at most 2 power cost, right? Let's say the cost is k, it partitions the space into 2 power k rectangles. Now let R subscript I be the 1 rectangles out of these, and where small I comes from the index set capital I. So Ri be the 1 rectangles. Okay. Now we have two things that I can easily say. Ri are the 1 rectangles in the protocol. Now you look at the measure of Ri intersection f inverse 0. So Ri is a 1 rectangle, and how much of zeros are there in Ri? That is what mu of Ri intersection f inverse 0 is doing, and then we sum it up over all the 1 rectangles. Basically, we want to see how many 1 rectangles, how many zero outputs, how many zero values are coming in, getting output as 1. So we know that the total error that is allowed by the distributional protocol is at most epsilon. So this contains both zeros being reported as 1 and 1 being reported as zeros. But here we are just counting or estimating the zeros being counted as 1. So altogether, all the errors, the measure of all the errors is at most epsilon prime. But even the measure of, if you just restrict it to the measure of zeros being reported as 1, that's also epsilon prime. So total error is epsilon prime. So even this measure of zeros in the 1 rectangles total is also epsilon prime. So that is easy. The second thing is, if you just take the sum of the measure of all the Ri's, the measure of all the 1 rectangles, you want it to be close to the total measure of ones in the entire matrix, right? Because if it is too far apart, then that itself means there are lots of errors. So how far apart can we allow to be? The error that is permitted is epsilon prime. So consider the total number of ones, and you subtract epsilon, or consider the total measure of ones, you subtract epsilon prime from this. The measure of the 1 rectangles, or measure of the rectangles that are reported as 1 should be at least this. Because if it is smaller than this, that means there is a gap of more than epsilon prime with the actual ones and the reported ones. So it cannot go smaller than this. Okay. So just once again, number 1 is, what is the total measure of the zeros that are being reported as ones? This corresponds to errors. And this, since the error is at most epsilon prime, this summation is also at most epsilon prime. Second is, what is the total measure of the 1 rectangles? If the total, when you compare it with the total measure of the ones, again, this cannot be too far apart because of the because the error is bounded to be epsilon prime. So it cannot go lower than the measure of the total number of ones minus epsilon prime. Okay. Now, I is the index of all the one rectangles. Let us define I prime as the indices, as a subset of I, that are the indices of the almost epsilon unbalanced one rectangles. Meaning, I prime contains exactly those indices that satisfy this inequality, that is the measure of the zeros should be at most an epsilon fraction of the measure of the entire rectangle. Right? This is what all the Ri's where I come from I prime satisfy. And for all the Ri's where I does not come from I prime satisfies the opposite. Does not satisfy this. So it violates this. So now let us consider the total weight of all the rectangles such for which I is not part of I prime. Okay, that is summation I not in I prime mu of Ri. Now, if I is in I prime, this inequality is satisfied. If I is not in I prime, we know that mu of Ri or epsilon mu of Ri is going to be strictly less than mu of Ri intersection F inverse 0. So epsilon mu of Ri is going to be less than this. So mu of Ri is going to be less than mu of Ri intersection F inverse 0 times 1 by epsilon. Basically, this epsilon goes here and the inequality gets reversed because it is not a member of I prime. And now we are summation I not in I prime, and that summation remains and it's multiplied by 1 by epsilon. And 1 above, so what is summation I not in I prime mu of Ri intersection F inverse 0? We don't know this, but we know that we take the summation over all the I in capital I. The summation is at most epsilon prime because of 1. And I prime is a subset of I. So this is also upper bounded by epsilon prime. So this entire summation is epsilon prime and there is a divided by epsilon. Thus we get this. Now let us compute the total measure of the rectangles that are almost epsilon unbalanced. Or in other words, the total measure of the rectangles is that I is in I prime. One easy way to compute that is take the total measure of all the one rectangles and you subtract the measure of the ones that are not in I prime. Right? And we know we have upper bounded the total measure of those rectangles that are not in I prime. So now this gives you a lower bound because of the negative sign. So, but before that, summation I in I mu of Ri by 2 is given by mu of F inverse I minus epsilon prime. So this gives you mu of F inverse 1 minus epsilon prime. This is by 2. And summation mu of Ri, I not in I prime, was upper bounded to be epsilon prime by epsilon. And here negation, so the inequality is consistent. We have this. So the total measure of those Ri's where I is in I prime is at least this. Okay. But remember we had this assumption that for each the maximum measure of an almost epsilon unbalanced one rectangle was alpha. In the present defined terminology, almost epsilon unbalanced one rectangles are those in I prime. So put together the size, the measure of the total rectangles in I prime is this, but each rectangle has size at most alpha. So the number of rectangles has to be at least, each rectangle can contribute at most alpha, and we know that this is the total measure is at least this. So we should have at least this divided by alpha many rectangles. That is the size of I prime. Now size of I prime is just the set of almost epsilon unbalanced one rectangles. There are other 1 rectangles, and then there are 0 rectangles. So this is this is smaller than the total number of rectangles, but the total number of rectangles is at most 2 times the cost of the protocol. So 2 times the cost of the protocol is at least the size of I prime, and size of I prime is at least this. So we have the cost of 2 power the cost of the protocol is at least this, which was what was stated here. We started with any distribution protocol where on a distribution nu and error parameter at most epsilon prime, and we showed that the cost satisfies this inequality, which was what we wanted to show. Okay. So just to recap, so now what remains is Stirling's thing. So, but I'd like to recap the thing again. Okay. So the first we proved the claim. What was the claim? The claim was that if S prime is large enough, then we have elements x1, x2, etc. in S prime, square root n by 3 such elements, such that each xi intersects with in at most square root n by 2 positions with the previous xi's. And how do we show this? We show it. We show it by induction. Consider L to be strictly less than square root n by 3. Now we have sets x1 to xl. The total number of elements contained in the union, so we call the union Z, is at most square root n by 3 times square root n, which is n by 3. Now what is the number of elements in S prime that intersect in at least square root n by 2 elements of Z? We count that, and that turns out to be this binomial, the sum involving binomial coefficients, and that gives us this, by Stirling's approximation, this bound, which is strictly less than the size of S prime. So that it must exist elements in X prime such that X intersection Z must be at most strictly less than square root n by 2, and that is what we are looking for, and that's what the claim asserts. And we can use this claim repeatedly till L is strictly less than square root n by 3. So we get up to square root n by 3 elements. Fine. Now we are going to show the just walking over the proof of the theorem. So the lemma was that if S cross T is almost epsilon unbalanced one rectangle, in other words, the fraction of 0 entries in this one rectangle is at most epsilon, then either S or T is at most 2 power minus c square root n times n to square root n. So now we will bound the size of the rectangle that satisfies this. So let's say T is a smaller one. So now the measure of R is the measure of summation of the measures of the elements in R. But then since it's a product distribution, we could just split it into the products. We have no bound on S, but we have the trivial bound that the summation of the measures will be at most 1. So we use that. And we know that the summation of the measures of the columns is upper bounded by 2 power minus c square root n. So recall that this n to square root n is the number of columns. So because and it is uniformly distributed, so that will not appear in the measure. It is just 2 power minus c square root n. So the measure of R is at most 2 power minus c square root n. Then we have the corruption bound, which says that if the maximum measure of an almost epsilon unbalanced one rectangle is alpha, then, and if we have an error parameter epsilon prime, which is strictly less than epsilon, then 2 power the distributional complexity is at least this. So now we proved the theorem using corruption bound. So where f is the disjointness function, epsilon prime is the parameter, alpha we've just seen alpha is at actually 2 power minus e square root n. So, and we already saw that the constant fraction of the inputs correspond to 1 inputs. So 1 by alpha is 2 power c square root n. The 1 inputs are 1 by e, and we can tweak epsilon prime and epsilon so that this is insignificant as compared to 1 by e. Taking log, we get the square root n bound for the disjointness function. And this translates to a square root n lower bound for the randomized complexity as well. Okay, corruption bound. First, consider protocol for F. This partitions the space into 2 power the cost many rectangles, or at most 2 power the cost many rectangles. Let Ri be the 1 rectangles. So first we count the fraction of the zeros in the 1 rectangles. This should be at most epsilon prime, the allowed error. Then we count the measure of the total total measure of 1 rectangles, and this has to be not too different from the total measure of ones. That gives us this. Now let I prime denote the indices of the almost epsilon unbalanced 1 rectangles, which satisfy this. Now we estimate the total weight of those 1 rectangles that are not in I prime, and that does not satisfy this, so we satisfy the opposite inequality. So we get that this is at most this divided by epsilon, and this summation is at most epsilon prime by 1. So we get this, and the total measure of those rectangles in I prime is, you can obtain it by a difference, and mu summation I in I mu Ri is given by 2, and this thing is upper bound by epsilon prime by epsilon. So we get this, and by assumption, so this is a lower bound on the measure of the total number of measure of the rectangles that are such that I is in I prime. But each rectangle has measured at most alpha, so the total number of rectangles must be at least this. Total number of rectangles in I prime must be at least this, hence the total number of rectangles must be at least this. So 2 power cost must be at least this. So the cost, so that's the statement of the corruption. Finally, we just go to the Stirling's approximation calculation. Again, it's this is, if you followed the yesterday's calculation, this is very similar. So we wanted to show n by 3 choose a square root n by 2, 2n by 3 is choose square root n by 2, strictly less than 2 power minus 1 minus c prime square root n times n choose square root n, right? And in fact, there was a square root n by 2 term outside, but since that's a single term and we are not dealing with the binomial coefficients, that can be ignored for now, and it doesn't really matter. It can easily be accommodated in the calculation. And this is a Stirling's approximation. M factorial is roughly equal to square root of 2 pi m times m divided by e whole power m. And since we are dealing with binomial coefficients, the e term will cancel, and this single 2 pi square root m also is something that we can ignore, just like we are ignoring the square root n by 2 here. So the only term that we need to bother about is m power m. So it is n by 3 factorial divided by square root n by 2 factorial times n by 3 minus square root n by 2 factorial. So we get this. Similarly, we get this and we get this. And first we take out these 3 terms, square root n by 2 whole power square root n by 2, same thing here, and square root n power n. So we get this here. Then we have the remaining terms, and I do some kind of rearrangement. So we take out, so what we have here is the reciprocal of the bottom part. I have taken it to the numerator. I take n by square root n, and the rest the other n is taken inside this. Similarly, These two terms also I have taken below the denominator. And the thing to note here is that, again, it's kind of hard to explain like this, but if you just work out, you can see how this is being obtained. This term is close to 1 because this is really small when n is large. Same thing here and same thing here. So what really remains? So this, by the way, here this boils down to 2 power square root n. And what really remains here is this 1 by n power square root n, 3 by n power square root n, and 1 by 2 power square root n by 2. So the n power square root n cancel, 3 by square root n in the denominator, 2 by 2 power square root n, and 1 by 2 power square root n by 2. So we have this. And here, if you notice, 2 power 3 by 2 is strictly less than 3. It's easy to see. 2 power 3 is 8. The square root of 8 is less than 3. Hence, this is some number less than 1 whole power n. So you could write it as 2 power some minus constant, where constant is a constant greater than 0 times square root n. And this is what we wanted to show. We wanted to show this. Again, there's the minus 1 here, which is not so difficult to obtain. You can get this, you can maybe reduce the constant a little bit and get minus 1. And instead, we have shown this and this divided by this is strictly less than 2 power minus constant square root. And that gives the bound here. And that completes the content for today. So I will stop.